All right, welcome everybody. We're going to start our last topic of this sort of thermodynamics chunk that we've been working through. At the end of class, if you haven't done so already, you could turn in your extra credit work. At the end of class, also, I'm going to end it probably a little bit early. I'm going to pass back your quizzes from last time. So quiz 3. Yeah. That. Get these out. Okay. All right.
Professor, before we start, I know next Tuesday we have an exam, correct?
Yes.
So it'll be everything starting from rotational motion all the way till this topic 12, correct?
Up till this topic, yep.
Okay.
So I'm going to try to get as far as I can today. So that way, next class on Thursday, I'll be able to review. I'll finish early, and I'll be able to review rotation, angular momentum, and then this big pass of thermodynamics, just like a review session, probably like half of next class. I'll be able to do that. Let's see. Yeah, and then it'll be Thanksgiving break, and then we'll have one more week. And then I'm thinking on the very last class, very last lecture, I'll have like a review session for the final. I think that'll be good. Yeah. All right. Let's go ahead and get started. We've been talking a lot about things that are heating up, cooling down, energy flow, this way, that way. Now let's actually start learning a bit about the laws of thermodynamics. We've already seen the zeroth law, and we've looked at ideal gases and way things are described, how pressure can change and how volume can change. That was all related to that ideal gas equation as PV equals nRT. But now, let's actually look at what we can get out of studying this topic. So, a lot of times when people are studying something, they want to see what the thing can be used for. This is the part of the whole thing where I've covered the bases, and now we see how we can actually use this change in energy, change in temperature, to actually produce something valuable to us. And we're going to look at work. If we could get some sort of gas to produce work, that will be a big benefit for us. And we know that some gases may expand, pressures change. All we have to do is change a temperature. Maybe we can use that to perform some kind of work. Let me try to get this thing ready over here. The biggest and best example of this is the invention of the steam train and how it can, shape the development of an entire culture. This thing right here, propelled us into the, through and onward through the industrial age, figuring out, how countries are run based off of who can, manage, maintain these things right here. But how does this sort of steam train actually work? Well, we get the steam. You see that large tank right there in the front, that big sort of circular thing in the front? That is just almost all full of water. And you've probably seen like a old show or a western or something where someone is at the front and they're just shoveling coal. And how are these two things, like coal, and I said that's water, how are they related? Well, that person at the front, they're shoveling coal into the furnace. They're making this big fire, this big oven. They're maintaining it at a certain temperature. They're turning all of that water in that tank into steam, into something that's very highly energetic. So, since they're increasing the temperature, they're going to increase the pressure. And I should have written this down first. By changing the pressure, we can actually produce work from this. So work is pressure times the change in volume. So this is work done on a gas at a constant pressure. If I get all that steam from that sort of boiler in the front, and I'm able to funnel it somewhere, able to have it push something for me, that can do a lot of work that it would take just hundreds of regular people to do. So we can have this pressure and volume difference do this sort of work for us. They could do force over distance, or force times distance. Yeah.
Professor?
Yeah.
Why is pressure negative in this case? Like, what does it mean?
So in this case, it's negative because imagine if so that's a change in pressure. I'm sorry, the change in volume right there. We have this still here. We have this balloon. It has a fixed pressure. It has a fixed volume right now. Volume is the size. A while back we talked about the actual number of molecules in here. That's different than volume. So volume is just the size. If I was to shrink this down, if I was to take this balloon and compress it down to the size of a golf ball, I am doing work on the gas. And so it'll go from a big volume to a little volume, and if we go final minus initial, it'll be sort of this negative volume, and so that's why we have that negative in front to cancel it. That kind of.
So it's because work is being done on gas.
Being done on the gas. This is where we also need to reflect on those definitions of work done on something and work done by something. So I'm going to be saying a lot of things like work done on the gas, work done by the gas. Yeah.
If the work was done by the gas, would the work be negative?
Yes. That's actually my next slide. So let's see. I'll do that on the next slide. Okay. So I like this little picture you have in your book. This thing we're used to is someone pushing something and displacing something. They're doing work in the direction of the motion. It's them moving the box. Same exact principle of someone compressing some gas. So they're applying work, they're applying positive work on the gas. So that picture up there is showing work done on the gas. And that is positive. That's positive work. And let's see. What was I going to do? I was going to draw. I don't want to draw another cylinder. Let's see. When we do compress something like this, we take this gas, same exact thing as the diagram above. We're compressing something. We are, what are we getting? We're getting a decrease in volume. And maybe there's a pressure increase because we have this work being applied on it. But that may not always be the case, so I'm going to say sometimes. I'm going to do the little squiggly for sometimes pressure may increase. And I'll say sometimes temperature may also increase. If we take this, I keep putting it away, balloon, and take all of the molecules in here, remember what temperature is. It's just the energy that is in the molecules that are sort of just flying around. And they're bumping into each other. They're creating this energy flow from one molecule into another. So if I take all of them and I compress it down to the size of a golf ball, all of those molecules flying around in there are going to be bumping into each other a bit more rapidly. So pressure may increase, and so temperature may increase as well. Okay.
So,
basically, yeah.
When work is done on a gas, the gas will expand, right?
Work done on a gas means we're compressing it. Let me also put that, right. Decrease in volume, it's getting smaller.
Oh, okay.
So I'll say over here, compression.
So on the steam engine example, work is being done on the gas, correct? Or
There are actually two different cycles for that steam engine example. That was just sort of a big, broad term example I was showing in the beginning. The work is actually being done by the gas. It's sort of, it's both, I should say. The person shoveling coal in is doing work on the gas by increasing the temperature and increasing the pressure. And then the gas is pushing the pistons back and forth, so expanding the volume right here. So increase in volume. That's the gas pushing on like those pistons and making the thing cycle, making the wheels turn. You can think of that. And of course, if something is, let me do it like this, minus work, pressure may decrease and temperature may decrease. All right. This is usually called expansion of a gas. Yeah.
If the work is zero because volume's constant, is the gas just in equilibrium?
Yeah. Yeah. You're like just like 2-3 slides ahead of me on this whole thing. I need to speed up. Okay. So actually I wanted to show you guys this in case you weren't here when I showed it the first time. This is a model kinetic theory apparatus. This model is just like the states of matter. I have some beads in here that are all, actually kind of organized right now. And if you look at something that's a solid, all the little molecules and atoms as they're connected together, they actually jitter a bit. because it has temperature. If something's jittering, something is held together like a solid, it's actually jiggling. And that's the object's temperature. That's how much internal energy it has. So when I turn this on, everything's going to start spinning, and that's just representing a solid. Then I'm going to increase the energy in the system. Therefore, I'm going to change this from a solid into a liquid, something that it's no longer in a rigid structure like this. Imagine the bonds start breaking here and there, and they turn into little things. Maybe this, maybe a little bit littler. They're able to flow past one another. Then if I increase the temperature more, I add even more energy, this thing will, all of these small bonds will break. They're free to go in any direction they want. And that's representing a gas. So, we have a solid, and by increasing the temperature, now we have a liquid. They're all free to go past one another. If I increase the temperature more, it's pushing on the wall. It's doing work on that piston right here. Turns into a gas. If I cool it back down, it's back to a solid. All right. Now, imagine that gas, it itself can expand even more than it's done so right here. So imagine, that steam train, if it had some water in it, that water can expand, and then the steam itself can also expand even more, doing a lot of work on the pistons that are involved. All right. So, let's see. Next we have first law of thermodynamics. Okay. So in general, we talk about thermodynamics. People want to have like a really rigid structure on what they call energy and where it's going and where it's being lost. At the time, when people were studying thermodynamics over here, other people were just studying regular physics over here. So these two sort of areas of science, they sort of had to do their own thing for a while in the very beginning. This is essentially the energy equation we had a long time ago. This is conservation of energy. So delta U right there, that's just saying change in energy. Let me say it again. Or I should say change in internal energy. That's a better way. Q is heat. That is sort of the process of adding energy to a system or having energy come off of a system. And W, that's the work done by the system. So how much work does that gas do on those pistons? Okay. And I've written over it, that's fine. This next part, I gotta just sort of introduce it right here because I didn't derive any of it up to this point. I didn't want to have to torture you guys through all that. For a monatomic gas, we are talking about ideal gases. There are different types of ideal gases. If the gas itself, I don't even have just like a regular ball. If the gas itself, imagine I was talking about this being some sort of molecule. Imagine just one of these red cylinders flying around, acting like this system right here. That's a monatomic gas. All of the particles are just seen as one single dot, or one single entity. Oftentimes, though, if you look at, or if you go more into chemistry, things don't stay by themselves that often. A lot of the time, particles may sort of bond together. You might see things like O2 or N2. Those are called diatomic gases, and they're sort of linked together. Something that kind of looks like this. For monatomic gas, we have that. I guess it's supposed to be the form of like that specific heat formula we've used a while ago. That way it's easier to remember. Remember, it was like delta Q, delta T. So it sort of mimics that form. But it's N, and that's the molar number, or number of moles of gas involved. So I guess you could say this right here is the same equation except for molecular level specific heat changing energy. Right. So this is the only slide I just kind of throw things at you. If you are, yeah.
I was going to ask, why is it 3 halves?
Why is it what?
3 halves.
3 halves.
Or 3/2, sorry.
I believe it's because of, let's see, the way the R is the universal gas constant, and I should have looked that up a bit more. I'm not quite sure right now. I do know you are going to be doing something with, say, like a diatomic gas, or you level up even more gas structures. So I was saying, like, if you had just regular oxygen flying around, that's monatomic. If you have O2, or maybe nitrogen, it's like N2. It's a diatomic gas. 2 atoms sort of bonded together. That will be something that looks like 5 halves. Five halves are, that's for diatomic. Yes. And whenever you add another molecule, another atom, it increases by 2. Or 2 halves. All right. Let's see, what else do I want to... Okay. So, now now that we looked at how a gas may be able to, push on a piston, apply some work just by changing its volume or changing its pressure, we can maybe visually make this easier. We're going to be using what's called a PV diagram, pressure versus volume diagram. And there are some things that will make this easier. Let me put that one up first. Let's see, we have pressure versus volume. And let's do that process again or what you brought up. If we keep the volume the same, say we have a constant volume. Say our volume's right there. We have a constant volume, but our pressure increases. Say we start right here. And our pressure increases. We will go up to that point. Right there. Let me put that work equation on here also. So, just by, let me do this. P1, P2, V1. Okay. By increasing the pressure alone, and if we kept the volume the same, we're not going to actually get any work done. We're not going to get any work out of this gas. So, what's something else we could try to maybe produce some work? Remember, work is, a force. Something has to actually move. So we could maybe keep the pressure the same, and we could increase the volume. That will make a straight line like this. So let me label these as like path A, there's path B. But these are actually already decided, or I guess fundamental parts of this PV diagram. These are sort of, how should I call them? They are essential, and so they've sort of been defined as a process of this PV diagram. So we have these four. I'll do a little picture of each. Volume isobaric, that's when the pressure stays the same. If you ever fly a plane or go hiking, you might need a barometer. That's something that tells you the pressure you currently are in, the air pressure. So this is saying constant pressure. So that is that first case I had right here. For an isobaric process, thermal process, we can maybe expect, oops, sorry, I did it wrong. Nobody caught me. So it's still good. Okay. Yeah.
So PV diagrams are for work done on the gas. So they can't be used for work done by the gas because area can't be negative. Is that?
So finding the work done is just the area under the curve.
Yeah.
Right. So it's really just, I can maybe show you when we get to the volume one right here, up next. it can go either way. You could show work done on the gas or work done by the gas. It just depends on which direction you're going. So I'll show you.
Okay.
All right, yeah. So isobaric constant pressure, I should have had one line right here. We have a constant pressure and pressure is constant, sure. Isovolumetric, yeah.
I apologize for asking certain questions, but what is the units for pressure and volume in this case?
I think they use pascals and
Meters.
cubic meters. Yeah.
I use meters, not cubic meters.
If it's the volume, it's going to be a cubic of some kind. Or it could be liters.
If you use, let's say, like, I don't know, like atmospheres and liters, would that change our answer quite a bit, or would it stay the same?
I think it should stay the same, relatively. Yeah. Isovolumetric, that is the one where the volume remains the same. So there's our start. Here's our end point. And for an isovolumetric process, we have volume is constant and no work can be done. As for your question on the work, so you'd look at this isobaric example right here, and it depends on if you're going from, right, so 1 to 2, or if you're going from 2 to 1. If you're increasing the volume, that means it's negative work because the gas is doing a work on its surroundings. If you are decreasing the volume, you're compressing it. That's this positive work. And it's still the same amount. It's still that same area under the curve.
So area should always be positive, it's just that work can be negative.
Right. So you can imagine it's like a cycle or a process that has a direction. So is it going to the left or is it going to the right? Same thing with this isovolumetric process. Is it starting really low and growing, or is it starting really high and shrinking? Does it have a direction? Which direction is it going? In that case over there, isovolumetric, it won't produce any work. Isothermal. That is something that's a bit more odd for this diagram. It's going to create something sort of like a slant, some sort of ramp. It's going to look like this. So everywhere on that solid line is going to be the same temperature. What I'm doing is let's see. We start out on the left side right here. We start out right here. This is a very low volume. It's very compressed. And, very low volume and a very low pressure. Low volume, high pressure. Okay, then as it changes its volume, as it starts to grow, the pressure will decrease and the gas inside will remain at the same temperature. So everywhere on this line is the same temperature. I'll say that's T1. And then everywhere on, I don't know, this line, if it's isothermal, everywhere on that line is a constant temperature. I'll say that's T2. These are called isotherms. You'd study this, I think, if you went into meteorology or maybe geography. Everywhere on that line, same temperature. Adiabatic, that's the tricky one. That's the one that, or let me actually put in this before I go to adiabatic. We have T is constant. And since the temperature is the same everywhere on that line, there's not going to be any change in internal energy. I'm not adding more energy to change that temperature. So delta U is 0. There's no change in internal energy. This is for that ideal gas. All right, so everything's been behaving really well so far. Isovolumetric, volume's constant. Isobaric, pressure's constant. It kind of flows nicely. Adiabatic is the problem child in that nothing is held constant. So I'll say nothing is constant. Since nothing is constant, also add this. There's no adiabatic processes are usually very, very, very quick. They happen almost instantly, and there's not going to be any heat transfer through the object. I have a little example, something that uses an adiabatic process right here. So they're usually extremely quick, and they can't transfer any heat to the surroundings. Let me draw this diagram before I forget about it. And it kind of looks like the isothermal, except it's a more dramatic slant downward. It goes like that. Whereas isothermal stays the same temperature, the adiabatic sort of cuts through where it might stay the same temperature. It might change temperature very rapidly. I have right here something that you might actually hold in like a survival kit. I have this little bit of fuzz, sort of like from a pillow. I only need a little bit. Put a little bit in here. And there's nothing else in this tube except for this little bit of like lint, pillow fuzz, and I'm going to have this plunger. It's got a little O-ring on it. It seals in the air. Right? Put that right there. Now, what I'm going to do is create an adiabatic process. I'm going to make this thing, I'm going to compress all of this gas in this tube very quickly so it doesn't have time to change temperature, doesn't have time to, what's the word I'm looking for? Distribute the heat into its surroundings. So what's going to happen is all of the heat that was going to be distributed somewhere is going to go into that material, into that sort of pillow length. It's going to happen really quick. Let everyone go go ahead and watch. Right there. Ready? 3, 2, 1. And we have a way to create this rapid change of energy has nowhere else to go. It's going to be going through this adiabatic thermal process. All of that heat had to go into that material here. I'll have to reset that. If I could do that again at the end of class. But that is something that you might keep in like a survival kit. You just get the little embers out of that, and you have a way to create a fire. All right, what else do I want to do? That. Okay. Heat engines. Okay. Before I get on the heat engines, I won't get a time to bring this up again. I have right here, it's called the love thermometer. Sort of sold in novelty store. You see right here, all of this liquid is resting in the bottom of this glass. It's got this nice little twist in it. All you have to do, the directions say, you just hold this and it will channel your love energy. And the water will go from the bottom chamber up into the top chamber. It's just about all up there now. Okay? How's that working?
Does that have to do with the temperature from your hand?
This is the temperature from, it didn't do it until I started holding it. So what's happening is there's only so much gas in this device. There's only so much liquid in the device. So when my hand warms up the gas, it has nowhere to go, so it's going to be trying to find where it should be going. It's going to be pushing the liquid out of the way, and so it ultimately pushes all of that liquid up to the top. Does it again.
Can you do it the opposite way by putting your hand on top and it goes down?
I don't know. Let's see.
Interesting.
That was a good idea. All right. You can come down and try out the love meter after class. For a heat engine, for something to actually use that work, that sort of process of pushing something, some sort of gas is in a tube and it's going to be pushing against the wall. It's going to be pushing against the piston. I have a little model of a actual piston inside of your car engine. Right here. Let's see which way you got there. Okay. So, do that. I'll press next. And I'll get ready for that. Okay. So, what's happening in an engine is it's going to take some sort of high temperature thing. Maybe it's some sort of high temperature, I don't know, stuff from gasoline. Maybe it's an explosion that is happening inside of this little chamber here. So in your car, there's thousands of little explosions. It sort of jets in a little bit of gas of gasoline. So just some vapor fills this chamber here. And then the piston compresses it. So the engine piston right here, it compresses it all the way up to the very top. So now it's very compressed. There's a very high pressure, and it's at that point your spark plugs at the top igniting. They send a little change of temperature. That makes this thing a little explosion, and that will push that piston down and give you power. So it depends on what kind of engine you have. You have several of these going. That provides power to your car. This thing's just going, constantly. I think there's supposed to be like a light. If I go fast enough, I'm going to do that. All right. So for a heat engine, it will always be going through this same cycle. It could be in a car, it could be in that steam engine I showed in the beginning class. It could be the engine of your body. It could be you as a human engine. You have a hot reservoir. That's basically like your stomach. Whatever type of object this is, it takes this energy that was originally hot and it gets work out of it. And then it disposes of the cold remaining bit of energy. Okay. So, we can actually calculate how much work an engine can produce. It could be any type of engine. It can be you or me or your car or airplane. The work done by an engine is equal to the net energy absorbed by the engine. So ultimately, it just comes down to this. I'm going to say work. I'm going to say ENG for engine is equal to the heat of that hot reservoir minus the heat of the cold reservoir. And if we were to compare this to, how does this look on the PV diagram? For this engine, it's going to be, you look at this system right here. Starts out with a big volume, and then it compresses it. So that's positive work. It's compressing something. But then, that's sort of the engine system is it's going to expand again. So it expands. It takes in new gas. Expands. So that's work done by the gas. It's expanding this piston. And then the cycle repeats again. So we have this circular, we have the cycle that's being created by all engines. And the area that's enclosed inside of that cycle is the amount of work that can be done by the engine. This will be useful if we want to figure out how efficient we can possibly make an engine. If we want to, outsell Tesla, get the biggest car brand, we want the most efficient engine. 200 miles a gallon. How many people would really like that? I would. That'd be great. You could drive for like, I don't go anywhere, I could drive for like a whole year on like one tank of gas. How do we make a more efficient engine? Well, we just look at the amount of work that it can produce, and we look at where is that sort of efficiency fading off. Where is it wasting energy? So we can look at this efficiency right here. We have the efficiency of an engine, I want to get this wrong, is equal to the work that it produces over the amount of heat that the hot reservoir contains. There's another form of this. I'll just write them all out. We can rewrite it as that equation above. Q hot. And these are absolute value signs. So it doesn't matter if it's positive or negative. It's always hot minus cold. Not hot again, it's cold. And if I sort of reduce this down one more step, we get something that looks like this. It's 1 minus cold over hot. Yeah. So if we want that most efficient engine, we want 200 miles to the gallon. We need to get this fraction right here. We need to get that to 0. That way it'll be 1 minus 0. It's 100% efficient. So it will use all of the energy I put into it. I think most cars are, I'm just going to guesstimate around, I think last I heard, maybe around like 40%. Where's all that energy going? Well, your car is, like I said, it's doing this really big explosion, compressing the gas, and lighting this, and it's going to be really hot at that moment. That is the hot reservoir, and it pushes it out, sort of producing this work, pushing it out your exhaust. You guys ever gone over and felt the exhaust pipe? That's not that cold, but it's much colder than this hot system. So we want something completely efficient. We kind of know the way, but it seems almost impossible. In fact, it is impossible to get something that is 100% efficient. I'll show that next class. We have one more slide. So let's see. Here's another kind of heat engine. You see inside here. I don't know if you can. Maybe I'll turn this on. This is an engine that can be produced. It can produce motion just off of very subtle temperature changes. Let's see if it's working. Okay. So inside, there's a really big sort of piston. It's something that's covering the whole bottom of this inside chamber. And what's going to happen is I'm going to heat up the gas inside of here, and it will force the piston to move. Hopefully you'll be able to see it. I don't want to get this over by my computer. So I have this sort of just warm cup of water, and maybe it'll get going, maybe it won't. I think we said this one was fiddly a while ago. Maybe it'll start getting going in a bit. I'll just leave it alone for right now. So we have, what was that slide? It was refrigerators and heat pumps. So a refrigerator is essentially just an engine that works in reverse. So all refrigerators, the ones, anything that will cool down an area. So not just a food one, your air conditioner also does this. So it takes the energy from one area and it does work to it. There we go. It brings work in and it pushes it out into the hot reservoir. So behind everyone's fridge, there are these pipes, and what's doing is it's running inside of your fridge, and it's becoming the same temperature as the inside of your fridge, and then it's coming out of your fridge, and it's pushing all of that energy out into your kitchen. So your fridge is actually making your kitchen warmer because it is separating the temperatures from inside of the box. All right. If that doesn't go, it's not the end of the world. I have another thing over here. That hopefully will go. So this is just a simple example of a heat engine, something that's producing a change of pressure, change of volume. I have this can, got 2 holes in it, no hole in the top, 2 holes in the side, I have some water in it. And I'm trying to heat it up. And just by changing the volume, all of that gas has nowhere to go. It's going to be pushed out of the whole thing. Okay. I didn't test this beforehand, so it might work really well. It might not. We'll see. Okay. All right. So, go like this. So I have a big tank of water that I'm going to heat up. And the gas in there, there's nowhere to go. We need to have like a competition. I think it would be pretty cool. See who can make the best engine. Like if you add fins or something, I don't know. Let's see.
Water does have a high specific heat
It
capacity.
does. That's right. I think this needs to be like a lab you guys do. That'd be cool. While we're waiting, does anyone have any questions?
Oh, I do. So
Yeah.
I know you were mentioning that it's almost impossible to create the most perfect engine.
Yeah.
I was just curious because I was reading about how scientists are trying to create like a nuclear, like using nuclear energy, like an
Yeah.
engine. Is that would that be like the ideal perfect engine?
So that's getting very close to it. Whenever we say something like a coal engine or a steam engine, here we go. All it's going to do for a nuclear engine, it's still just going to boil water. So even in a submarine, it just boils water to make a piston go around and around.
That's the same way nuclear plants work? Nuclear plant?
Yeah.
Same thing?
Yeah, so they're just getting water really hot to make steam. So if you see plumes coming out of a nuclear power plant, they're just boiling water.
But it can't be perfect because heat's released into the environment,
Right, yeah.
Then we can contain that heat, right?
you know.
Or is it not possible?
So it is trying to turn. All right. I think I'll work on this a bit more. I'll come back with a better one. It is trying. All right. So I'm going to pass back your quizzes. And don't forget that there is homework due on Friday, midnight.